Okay, well, by now I'm sure you've recognized the similarity between the equations for angular kinematics and the equations for one-dimensional kinematics that we learned in the beginning of the semester. Let's finish the comparison. V equals V naught plus AT becomes omega equals omega naught plus alpha t. Delta x equals 1/2 V naught plus V times t becomes delta theta equals 1/2 omega naught plus omega times t. Delta x equals V naught t plus 1/2 AT squared becomes delta theta equals omega naught t plus 1/2 alpha t squared. And the last one, V squared equals V naught squared plus 2a delta x becomes omega squared equals omega naught squared plus 2 alpha delta theta. And you've also seen the equation for rotational kinematics versus the equation for translational kinematics. 1/2 mv squared versus 1/2 I omega squared. It turns out there's quite a few analogous equations that we're going to see over the next couple of chapters. So first, let's just make a statement of analogous quantities. In linear motion, displacement delta x is replaced with angular displacement delta theta. Velocity is replaced with angular velocity. Acceleration is replaced with angular acceleration. Mass is replaced with rotational inertia. And then there's a couple other quantities we should state here. Force is replaced with torque, and momentum is replaced with angular momentum. Remember that I represents moment of inertia. Also fair to call it rotational inertia. So let's just state a few equations. It works out that if there's an equation you already know for linear motion, there's a rotational counterpart that follows the exact same form. So for example, when we were done with our study of kinematics, we moved on to a study of Newton's laws. And the most fundamental equation we've learned all semester long says the sum of all external force is equal to the product of mass and acceleration. We can state that as a vector equation. So there's an analogous equation for the study of rotational motion that says the sum of all torque external, which is a vector quantity, is equal to, so we replace m with its counterpart, rotational inertia, and we replace a with its rotational counterpart, angular acceleration. Okay, what are some other equations we've encountered? In our study of work and energy, not only did we learn about rotational kinetic energy versus translational kinetic energy, when we were first studying energy, we learned how to calculate work. We said work is equal to the integral of f dot ds. So we're going to replace that with an equation that says work for things that move in circles is the integral of, and you can probably guess, torque dot d theta. And remember, work is a scalar quantity found when you take the vector dot product of force and displacement. Torque is a vector, angular displacement is a vector, but the product of the two, when taken as a dot product, gives you a scalar quantity. Okay, what else have we learned? Momentum. Momentum is nothing more than an object's total quantity of motion found by multiplying mass times velocity. Angular momentum is found by multiplying rotational inertia times angular velocity. And we've also learned about the impulse momentum theorem that says impulse is equal to change in momentum, or better yet, the product of force and time is equal to mass multiplied by change in velocity. Well, that's replaced in our study of rotation with an equation that says torque multiplied by time interval is equal to rotational inertia multiplied by change in angular speed. So let's circle or highlight these new equations. We're already getting familiar with an equation for rotational kinetic energy. In the next chapter, we'll study torque and angular momentum and a substitute for the impulse momentum theorem when it comes to objects that rotate.